Hello everyone, and welcome to our video on sequences and series. So let's start right off with the definition. An infinite sequence is a function whose domain is the set of positive integers. The function values, written as a sub 1, a sub 2, a sub 3, ... a sub n, are called the terms of the sequence. The nth term, a sub n, is called the general term of the sequence. So you can think of this just like you think of regular function notation. Right? F of 1 is just a sub 1, f of 2 is a sub 2, f of n is a sub n. So this is just a function whose domain is the set of positive integers. That's what makes it a sequence. So in other words, we only allow plugging in numbers that are positive integers, and sometimes 0, so which we've noted here. So that's something to consider. The domain of a function consists of only the first n positive integers. The sequence is then called a finite sequence. So if we only include a fixed small number of positive integers, it's a finite sequence. I say small, but I mean small in the sense not infinite. And sometimes we include 0 in the domain, which would have us start at a sub 0. So a sub 0, a1, a2. So that's usually for things like programming, for example, when you write programs, because you talk about things in terms of bits which are off or on, zeros or ones. Then you usually start initially with a 0 being your first term, so to speak. Now keep in mind, if you're starting with a sub 0, then the nth term in this case is actually a sub n minus 1, because you have that additional 0th term. Okay, so let's just go ahead and tackle a quick example here. Right, the first 4 terms of the sequence a sub n equals 2n plus 1. So this is just plugging numbers into functions like we've done a million times, right? A sub n is 2n plus 1, so a sub 1 means plug in 1 in place of n. Nothing new here. 2 times 1 plus 1 is 3. A sub 2 is 2 times 2 plus 1. That's 4 plus 1. It's 5. A sub 3 is 2 times 3 plus 1. That's 7. And a sub 4 is 2 times 4 plus 1. That's 9. Example 2. Write the first 4 terms of the sequence a sub n equals negative 1 to the nth power times 3 to the n minus 1 power. So we take negative 1 to the first power times 3 to the 1 minus 1 power. Negative 1 to the first power is negative 1 times 3 to the 0th power. 3 to the 0th power is 1. Negative 1 times 1 is negative 1. Now we look at a2. That's negative 1 squared. 3 to the 2 minus 1 power. Negative 1 squared is positive 1 times 3 to the first power, which is 3. Now one thing I want to point out here, because this is going to come up a lot, is notice that this negative 1 to the nth power is always going to alternate between being equal to negative 1 and equal to positive 1, right? So now when we look at a3, for example, we get negative 1 cubed times 3 to the 3 minus 1 power. Negative 1 cubed is negative 1. And then this is 3 squared. That's negative 1 times 9. It's negative 9. So what we should see here is that whenever we have a negative 1 to a power like that, to the nth power, or it could be n minus 1th power or n plus 1th power, whenever we have that expression, our terms are going to alternate between negative and positive. So just something to kind of put in the back of your head for now. All right, now we look at negative 1 to the 4th power times 3 to the 4 minus 1 power. Negative 1 to the 4th power is 1. 3 to the 4 minus 1 is 3 to the 3rd power. 3 to the 3rd power is 27. All right, that's it for that one. Okay, so now we're going to move on to introduce a different notation here that we're going to use a whole lot. So this notation comes up a lot in any sort of probability type problems. Like for example, if you ask yourself, I have 4 different objects and I want to decide how many ways I can order them, right? Well, for the first object, you can pick 4 different things. Once you've picked your first object, each of those ways you could have picked that object, there's going to be 3 more objects to pick. And then once you've picked those first 2, there's 2 objects left to pick. And then there's only 1 object left to pick. So the product that we get here is the number of ways I could have ordered those 4 objects. So we give this a special notation. We would call this 4 factorial. So take a look here. The definition for any positive integer n factorial, written n exclamation mark, is defined as n factorial equals n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. So some additional examples. 5 factorial, that's 5 times 4 times 3 times 2 times 1. Multiply that out, what do you get? You get 120. 1 factorial is just 1. So this definition notation is not perfect, but it should be clear that what we mean here is you multiply every integer starting with whatever n is, and you multiply down those integers until you get to 1. So if we look at 1 factorial, then 1 factorial is of course just 1. And lastly, for the special case of n equal to 0, we define 0 factorial as equal to 1. So I'll try to illustrate why that is here real quick. So why do we define 0 factorial as 1? Well, let's take a look back at this previous example. We said 4 times 3 times 2 times 1 equals 4 factorial. But notice we could have also written 4 times 3 times 2 times 1 as 4 times 3 factorial. And similarly, I could write 5 factorial, which is 5 times 4 times 3 times 2 times 1, as 5 times 4 factorial. Right, I'm just taking this part, writing it as a factorial, and leaving the 5 out in front. That manipulation is actually a really useful algebraic manipulation, and we'll see that as we work through some problems with factorials. So, because I like to use this manipulation so often, or I should say everybody in mathematics uses this manipulation so often, what we want to be true is this statement in general. In other words, when I say n factorial, I want that to always be equal to n times n minus 1 factorial. So, call this a fact, right? So the only thing that could mess it up is when n equals 1, I would get a 0 factorial here. So let's see what happens when n equals 1. I should get 1 factorial equals 1 times 1 minus 1 factorial. So 1 factorial equals 1 times 0 factorial. So 1 factorial should be equal to 0 factorial. So in other words, if we want this statement to always be true, just like it was for these numbers bigger than 1, right? 4 factorial equals 4 times 3 factorial. 5 factorial equals 5 times 4 factorial. If we want to make sure that's also true when n equals to 1, then we just have to define 0 factorial as being equal to 1, since 1 factorial is equal to 1. So it's sort of an odd little situation, and again, it's mostly a convenience factor, because otherwise every time we wrote this statement, n factorial equals n times n minus 1 factorial, anytime we use this fact, we'd have to go, unless n equals 1, which we don't want to do. So in order to avoid that special consideration, we just say, well, we can define 0 factorial to just be 1, and then we don't have to worry about that weird special case. Okay, hopefully that makes some sense. So let's go ahead and start diving into some examples here. So example 3, write the first 4 terms of the sequence, a sub n equals n over n factorial. So a1 here is 1 over 1 factorial, which is 1 over 1, which is 1. a2 is 2 over 2 factorial. That's 2 divided by 2 times 1, which is just 1. a3 is 3 over 3 factorial. That's 3 divided by 3 times 2 times 1. And then I notice I can cancel that factor of 3. That leaves me with 1 over 2 times 1, which is 1/2. And finally, a4. That's 4 divided by 4 factorial. The 4's cancel, and I get 1 over 6. Okay, so we just solved this problem. We're done. That's totally fine. But what I wanted to point out here is that if we realized that we could apply this fact from before here, we could have made this process of writing the terms of this sequence simpler, actually. We could have said, hey, a sub n is n over n factorial, but n factorial is n times n minus 1 factorial. N over n cancels and leaves me with 1 up top, so this simplifies to 1 over n minus 1 factorial. So now if I did the same problem with this, I'd have 1 over 0 factorial for a1, which is 1 over 1, that's 1. For a2, I would have 1 over 2 minus 1, that's 1 factorial, it's 1 over 1. For a3, I would have 1 over 2 factorial. 2 factorial is 2 times 1, which is 2. That's 1/2. And a4 would be 1 over 3 factorial. Just 1 over 3 times 2 times 1. That's 1 over 6. So point being here was just that when we look at a problem like this, being able to use this general fact to simplify the expression first actually makes the computation easier than it would have been otherwise. And that comes in handy very often when dealing with these factorials. Okay, so with that, let's go ahead and look at another factorial expression to simplify. But I'm going to kind of do some other examples off to the side here to just illustrate this idea with real numbers before digging deeper into the more general expressions. So let's take a look at some just real number examples of simplifying these things. So call this bonus examples. If I have 6 factorial divided by 5 factorial, I'm going to write a lot more than I need to right now just to illustrate this. 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. I could do this. This is really time consuming. And then I get left with 6, right? But I could have also said 6 factorial divided by 5 factorial. 6 factorial is 6 times 5 factorial divided by 5 factorial. So notice, now, instead of rewriting the whole 6 factorial expression and the whole 5 factorial expression, I'm just noticing that 6 factorial is 6 times 5 factorial. So now I can just cancel that immediately and get left with 6. Okay, so let's do another example. Let's say I have 3 factorial divided by 4 factorial. So again, 4 factorial, that's 4 times 3 times 2 times 1, but that's just 4 times 3 factorial. So that's 1 over 4. Now you might have bigger gaps between your numbers than that. So maybe I have something like 5 factorial over 7 factorial. So what I'm going to do here is go, well, hey, look, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. But why would I write all of that when I can just notate it as 5 factorial? And then I see that, oh, I can simplify 5 factorial over 5 factorial. Cancels. I get 1 over 7 times 6, which is 1 over 42. So hopefully that illustrates the idea of using these factorial properties to rewrite your factorial expression in a way that simplifies much easier. Now we have to deal with that in terms of more generic formulas of n. So when we take a look at this expression, 2n plus 1 factorial divided by 2n minus 1, let's take a look back here and think about how we made the choices we made. Notice that when I started doing the more simplified version of this, I'm always taking the larger number and expanding it, because if I have 6 factorial here, 5 factorial is going to be one of the sub-factors, right? Like when I write out 6 times 5 times 4 times 3 times 2 times 1, I've got 6 times 5 factorial. Same thing here with the 4 factorial. It gives me 4 times 3 factorial. In other words, I always want to write out and expand the factorial that's the larger number, because it's going to contain the smaller factorial in it. So when I look at 2n plus 1 and 2n minus 1, which one's bigger? Oh, 2n plus 1. So I'm going to expand that 2n plus 1 factorial. So I'll leave my denominator the same. And so what's my first term? It's whatever's inside here, 2n plus 1. And then I multiply by the next integer down, right? 6 times 5 times 4. So what's the next integer down? Well, it's whatever 2n plus 1 was, minus 1. Which is, of course, just 2n, right? This is really just 2n. And then what's the next term? It's whatever that was, minus 1. That's 2n. Minus 1. Oh, but I'm going to be multiplying by all of the integers down to 1 here, which is the same thing as 2n minus 1 factorial. So now these cancel, and I get left with the 2n plus 1 times 2n, right? Because this expression simplifies to 2n. That's, when I distribute that, that's 4n squared plus 2n. So again, this idea here is just like when I did this expansion with 5 factorial over 7 factorial, right? I did 7 times 6 times 5. Oh, and the rest of this is just going to form a factorial. So I'll just write it as 5 factorial because that'll cancel. I did the same thing here. Started with the number inside, 2n plus 1, times that number minus 1, times that number minus 2. And that gives me 2n minus 1 here. Oh, well, the rest of it's going to make a factorial, so I just cancel it. Okay, so hopefully that made sense. Let's go ahead and move on here. So now we're going to start taking a look at recursive formulas. So a sequence is defined recursively when an initial term or terms is defined and further terms are defined in relation to those previous terms. In other words, you're going to be given one or two or a few terms explicitly, and then you're going to be given a formula for how to relate your terms together after that. So we'll take a look at the Fibonacci sequence as an example of a classic recursive formula. So we start out by defining the 0th and the first term for the Fibonacci sequence. A0 is 1 and A1 is 1. And so we'll kind of, we'll start listing these off to the side here as we go. Now, if I know A0 and A1, what I want is A2. So I'm going to take and apply my formula to this expression, right? I'm going to just plug 2 in here. A2 equals A2 minus 1 plus A2 minus 2. But A sub 2 minus 1 is really just A1, and A sub 2 minus 2 is really just A0. And I already know what those are. That's 1 plus 1 is 2. I'll underline each of the new terms in our sequence expression here. So now if I want to look at A3, well, I apply 3 as n in my formula, I get a sub 3 minus 1 plus a sub 3 minus 2. That's really just a2 plus a1. What's a2? a2 was 2. We found that in the last step. a1 is 1. 2 plus 1 is 3. Now we'll look at a4. That's a4 minus 1 plus a4 minus 2. That's a3 plus a2. a3 was 3. a2 was 2. 3 plus 2 is 5. And so what do we see when we take a look at these? Well, what this formula is actually telling us to do is you find the nth term by adding the two terms right before it, right? I find the second term by adding the first and 0th term. I find the third term by adding the second and first term. I find the fourth term by adding the third and second term. So this formula says, for any nth term, take the n minus 1 term and the n minus 2 term and add them. In other words, add the two terms right before n. And that's what we see we've got here. 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, so forth and so on. Okay, so now let's go ahead and take a look at the general term a sub n for the sequence. So we're given a sequence, and we're assuming that n begins with 1, and we're asked to find a general term for the sequence. Now, this can seem pretty tricky, how to pull a formula out of your hat, but it's really just pattern recognition, and there's some things we can do to sort of make it easier. And it basically comes down to thinking about basic arithmetic. So when I take a look at this expression up here, I'm going to analyze my formula one piece at a time, right? Clearly my formula needs to be a fraction, and I'm going to look at the numerator first. So when I go from 2 to 3, what am I doing? Well, I'm adding 1, and I'm looking for something that's happening that's the same at every step. From 2 to 3 is plus 1, from 3 to 4 is plus 1, from 4 to 5 is plus 1. So I can really think of this as repeated addition of 1, and repeated addition means multiplication. So this I can write as 1 times n. But notice that if I start with n equal to 1, I should get 2 here. So I have to make a little adjustment to my formula to basically shift it, plus 1 or minus 1, whatever, to get me to this number. So when n equals 1, 1 times 1 is 1. I need to add another 1 to get me to 2. Okay, so let's check my numerator so far. When I plug in 1, what do I get? 1 times 1 is 1, plus 1 is 2. That's what I want. Check another value just to make sure you got it right. So here for n equals 2, and sometimes it helps if you label these things. Right, that way I'm thinking about my n value for each term. Okay, so when I look at my n equals 2, I get 1 times 2 plus 1 is 3. Okay, looks like we're good there. And now we need to do the same process for the denominator. But again, when I look at the denominator, I'm adding 1 at each step. So that tells me I should have, again, repeated addition is multiplication. So I should have 1 times n. But I need to start at 3. So when n equals 1, I should get 3 here. 1 times 1 is 1, plus 2 gives me 3. And now again, you can plug in your n values to check your denominator and make sure that it works. So what do I get when I plug in n equals 1? I get 3. When I plug in n equals 2, I get 4 in the denominator. Plug in n equals 3, I get 5. Okay, we're good to go. And now I'll just write this a little cleaner. This is just n plus 1 over n plus 2. Okay, another example. Write a general term, a sub n, for the sequence. Assume that n begins with 1. So when we do that for this one, the first thing we're going to notice is this -1, or this negative alternating. Negative, positive, negative, positive. So we want to figure out which expression to use for that. So we have a couple options here. We can use -1 to the nth power, -1 to the n plus 1 power, or -1 to the n minus 1 power. Now, not all of these will work. That's not what I'm suggesting. But what I'm saying is any of these types of forms are what we're looking for. So we just have to figure out which one is appropriate. So I'm going to use different n values here just to kind of chart out which of these makes sense. And generally, once you see this, I think you won't really have to go through this much thought process. You should be able to just look at it and figure it out. But the first time, I want to be really clear with what's happening here. So when n equals 1 here, I get -1 to the first power, that's -1. When n is 2, I get -1 squared, that's 1. When n is 3, I get -1 to the third power, that's -1. Now when I look at -1 to the n plus 1 power, plug in 1, -1 squared, that's 1. Now plug in 2, I get -1 cubed, that's -1. And plug in 3, I get -1 to the fourth power, that's 1. And then -1 to the n minus 1 power? Well, if I plug in 1, what do I get? I get 0, so -1 to the 0th power, that's also 1. If I plug in 2, I get -1 to the first power, that's -1. And if I plug in 3, I get -1 squared, that's 1. The key thing here is that I want everybody to realize that these are the same. Let me try that again here. So with this pattern, if you're starting positive, then negative, then positive, you can use either -1 to the n plus 1 power or -1 to the n minus 1 power. It doesn't matter which one you use. They give you exactly the same thing, right? So either one is fine. But in this case, we want negative, positive, negative, negative, positive, negative. So that part of my expression should be -1 to the nth power here. Okay, so now what I need to figure out is what to do with the rest of this. We go 3, 6, 9, 12. When I go from 3 to 6, I'm adding 3, and from 6 to 9, I'm adding 3. And then from 9 to 12, I'm adding 3. So repeated addition is multiplication. So this should look like 3 times n. And just check your first value for n. When n is 1, what should I get? I should get 3, right? 3 times 1 is 3. So that's fine. We don't have to add or subtract anything there. And that's it. That's my whole expression. Done. So, of course, with this alternating term here, the -1 to your power, I just want to reiterate that you don't need to write out this whole chart every time. It should be enough to just check the first term. When n equals 1, do you get a -1 or a +1? And check that with your sequence. Whichever one matches up is fine. And again, with these last two expressions, you can use either. They're totally equivalent, so it doesn't make a difference. Okay, so let's take a look at another example of a recursively defined sequence. So we're going to write the first 5 terms of this recursively defined sequence. We're given a1 is -4. Now we want to find a sub n plus 1 equals -3 times a sub n minus 5. So in this case, our formula is a little bit different because we're actually given a sub n plus 1 as the left side of our equation, but we have a sub n we have a1 to start with. So if I look, when I plug in n equals 1, that's going to go on this side of the formula. So it doesn't change much. We'll just start by plugging in n equals 1. That gives me a2 equals negative 3 times a1 minus 5. So that's negative 3 times negative 4 minus 5. That's 12 minus 5 is 7. And now we'll look at n equals 2. Plug in n equals 2, I get a sub 3 equals negative 3 times a2 minus 5. That's negative 3 times, well, a2 was 7, right? a2 equals 7 minus 5. That's negative 21 minus 5. That's negative 26. All right, now we'll look at n equals 3. So plug in 3, I get a4 equals negative 3 times a3 minus 5 equals negative 3 times negative 26 minus 5. Negative 26 times negative 3, that's going to be a positive 78 minus 5, that's 73. Okay, n equals 4, that's going to give me a5 equals negative 3 times a4 minus 5. That's negative 3 times 73 minus 5. Okay, negative 3 times 73. Well, 3 times 70 is 210. 3 times 3 is 9, so that's 219, but negative, minus another 5. So negative 219 minus 5 is negative 224. Hopefully I didn't make any silly mistakes there. All right, now n equals 5 gives me a6. Oh, wait, I don't need n equals 5 because I already have a1. And now I've got the other 4 terms, so I've got 5 terms. We'll stop there. Okay, so now let's go ahead and start touching on a different topic, and that's the topic of summation notation. So oftentimes in applications, we have to add a whole lot of numbers together, but those numbers can all be related to each other by some sort of formula. And so that allows us to take that sum of a lot of numbers and write them in a nice compact form. So that's the whole purpose of this summation notation, is being able to write complex sums in a nice compact form. So definition, the sum of the first n terms of a sequence, a1, a2, a3, etc., is denoted by sigma from I equals 1 to n. So that's what this symbol is. That's the Greek sigma. But we just think of this as the sum. This is the notation we always use for sum. So the sum from I equals 1 to n of a sub I, which means whatever formula you have here will be a function of I, and you're just going to plug every number starting from 1 up to n and add those together. So the letter I in the summation notation is called the index of summation, right? In other words, it's your variable for the summation. N in this is called the upper limit. It tells you when to stop adding things together. And 1 in this case is called the lower limit of the summation. Now, your lower limit doesn't have to be 1. You could start with a number other than 1, but most commonly we'll start with the number 1. So let's take a look at a simple example. Find this sum. So our formula here, this is a sub I, is 3i plus 1. And so what we're doing is taking from I equals 1 to I equals 3, and I'm adding all of these things. So let's write them out. When I equals 1, I get 3 times 1 plus 2. Plus. Okay, what's A2? Well, I just plug in I equals 2. That's 3 times 2 plus 2. Plus. And now for A3, what do I get? Well, I take I equals 3. It's 3 times 3 plus 2. And we stop there because that's our upper limit. It tells us to stop when I becomes 3. And now I just add all of those together. 3 times 1 plus 2 is 5, plus that's 6 plus 2, that's 8. That's 9 plus 2, which is 11. That's 13 plus 11, that's 24. Now, in the case of this sum, we've done this in long form, let's call it, and actually plugged in every value and added them together. But part of the advantage of summation notation is that we will learn that many types of sums have nice formulas that we can work with that save us a lot of computational time. So it's pretty rare that you're going to add all these out long form. That's not going to usually happen all that often, but it does happen on occasion where you just need to add them. Okay, so let's take a look at another example here. Find the sum from k equals 3 to 5 of 4. So this is a3 plus a4 plus a5. But the key to understanding this problem is realizing that I'm just taking the number 4 and adding it over and over. There's no k in my formula, right? So I'm not plugging k in. It's just for each value of k, starting at 3 and ending at 5, I'm adding the number 4 over and over. So 4 plus 4 plus 4, that's 12. All right, find another sum. We've got from k equals 2 to 5 of -1 to the k plus 1 power times k. So this is going to be a2 plus a3 plus a4 plus a5. Plug in 2, I get -1 to the 3rd power times 2. Plus, now I plug in 3, I get -1 to the 4th power times 3. Plug in 4, I get -1 to the 5th power times 4. And plug in 5, I get -1 to the 6th power times 5. This is -1 times 2, that's -2. Plus, -1 to the 4th power is 1, times 3 is 3, plus, -1 to the 5th power is -1 times 4, that's -4, plus, and -1 to the 6th power is 1 times 5. Okay, -2 plus 3 is 1, minus 4 is -3, plus 5 is 2. All right, that's it for that sum. So now we're just going to look at a summary of summation properties and some justifications for why they are what they are. So this first one, the sum from k equals 1 to n of a constant is just the constant times n. So in other words, if I have the sum from k equals 1 to n of c, that means add the number c together by itself n times, and by definition, that's the multiplication of c times n. So as a little like side example, we can basically say, hey, if I look at k equals 1 to 3 of 5, this is just 5 times 3, which is 15. Right? So this is an example where we can save a little bit of time computing a summation by just realizing we can apply a simpler formula. Now, if we look at the second property, we've got the sum from k equals 1 to n of a constant times a sub k, and we can pull that constant in front of the summation. This is just a shorthand for factoring, just a shorthand for common factoring. So if I look at the summation and I write it out long form, I get C times A1 plus C times A2 plus ... plus C times AN. So C is a common factor for all these terms, and I can factor the C out, and I get C times A1 plus A2 plus ... plus AN, which is just C times the sum from k equals 1 to n of A sub k. And now we look at our third property, k equal 1 to n, the sum from k equals 1 to n of AK plus BK is the sum from k equals 1 to n of AK plus the sum from k equals 1 to n of BK. What this essentially says is really that we can add in any order. This is just the shorthand summation notation for saying you can add in any order. So let's take a look. When I write this sum out long form, I get A1 plus B1 plus A2 plus B2 plus ... plus AN plus BN. But if I want, I can change the order I'm adding in and put all my A's together first, plus all of my B's together. And then when I write those in sum form, I get the sum from k equals 1 to n of AK plus the sum from k equals 1 to n of BK. Okay, 4, I didn't write out a justification for this because it's just subtraction of terms, and subtraction is just adding negatives. So this property is really the same thing as property 3. It's just adding negative values. And finally, our last summation property here is that the sum from k equals 1 to n of AK is equal to the sum from k equals 1 to j of AK plus the sum from k equals j plus 1 to n of AK. That seems tricky, but actually all we're saying here is that if I take my sum and I write it out long terms, I can add the first j terms, and then I could add the rest of the terms. And I'll get the same thing if I take those two things and add them together. So that's what we've done here. We've took the first j terms and added them together, and then we took all the terms that were left, starting with j plus 1 and ending with n, and we added those together, and that's the same thing. All right, so let's go ahead and do an example of writing a sum in summation notation. And the idea here is basically exactly the same as what we've been doing, but sometimes you get a little something tricky in your expressions. So here I want the sum of all of these terms, and I notice some patterns, right? Like my numerator is always 2 except for my first term. And in my denominators, I get 2 times 3 and 3 times 4 and 4 times 5. So my factors in my denominator are each increasing by 1, except in this first term. But oftentimes what you'll notice is that you can rewrite your first term to look like the rest of this. So I could have rewritten this as 2 over 1 times 2. And now if I look, that's still equal to 1, but now it matches the pattern of the rest of our expressions. And so that's going to make it a little easier to find our general term. So now instead of just listing all these things, we're summing all of these things from I equals 1 to, in this case. So, well, let's figure out what, if I is 1, what do we notice? First term, second term, third term, fourth term. So this must be the 9th term, right? So that tells us that we're stopping at I equals 9. Okay, and in our formula, our numerator is always 2, so I can just write 2 there. And our denominator, the first factor is I, and the second factor is always 1 larger than I, so we can just write I plus 1. And there we go. Okay, now we'll touch on one last topic here, and this is really just going to be kind of an introduction of an idea, just to kind of get it into the back of your head so that when it comes up later, it's not completely new. This is the idea of a series. So let A1, A2, A3, ... AK ... be an infinite sequence. then the sum of all terms of the sequence is called a series and is denoted by a1 plus a2 plus a3 plus ... equals the sum from I equals 1 to infinity of a sub I. The sum of the first n terms of the sequence is called the nth partial sum of the series. So we've been dealing with this already. We were looking at summation notation, but this is just an extra terminology. When we're thinking about this in terms of series, if we look at just adding the first n terms, we call that an nth partial sum. Now, here's something to consider. When I look at this sum to infinity, of course, we can't actually add infinitely many things together. And that's not what this notation means. So if we denote the partial sum here as S sub n, then what we mean by this infinite series is actually the limit as n goes to infinity of the partial sum. In other words, what values are the partial sums approaching? That's the question. So we're going to go ahead and look at an example here that hopefully should illuminate this idea a little bit. So we're going to consider the following series, the sum from I equals 1 to infinity of 1 over 2 sub I. And we're going to do this by looking at the partial sums. We're also going to look at this thing on a number line, and then hopefully we build some intuitive sense of what we mean by this idea of series. So if I take the first partial sum, that means just add the first term. Well, that's just 1 over 2 to the first power. Done. Now, if I take the second partial sum, that means you add the first and second term. That's 1/2 plus 1 over 2 squared, which is 1/4. That's 3/4. And now if we take the third partial sum, that means add the first three terms. 1/2 plus 1/4 plus 1 over 2 to the third power. That's 1/8. Okay, 1/2 is 4/8. 1/4 is 2/8. 4/8 plus 2/8 plus 1/8 is 7/8. And we'll write out one more of these, and then we'll start looking at a number line and see what's happening here. So our next term will be 1 over 16, and when I add these all together, I get 15 over 16. So now let's look at a number line. We'll go from 0 to 1, and we're going to plot each of these. So we've got 1/2, that's S1. Let's go ahead and mark the graph first. So 1/2, 3/4, 7/8, 15 over 16. And what do we see? So our sums, each time we add an extra term, the sum splits the difference towards approaching 1. And so the next term will be here, and the next term will be here, and the next term will be here, and so forth and so on. So the question we ask ourselves is, what value are these partial sums approaching? What number are all of the sums getting arbitrarily close to? And they're splitting the difference between whatever the previous sum was and the number 1, so they're going to keep getting closer and closer to 1. So these partial sums are approaching 1, and that's what we mean when we ask, what is the value of the series? We're asking, what number are the partial sums approaching? Right? So this series is equal to 1. Now, what we'll see in our later section is one type of series that we can evaluate with a nice set of formulas. But for now, we just wanted to introduce this idea and get the general idea of what a series is and what it means. All right, well, that's it for this video. Thank you for watching.